Okay, so today I'm going to be talking about the time independent Schrodinger equation, and this is just going to be a quick derivation video. So, pretty much, how we're going to start with this time independent Schrodinger equation is by using a differential equation technique called separation of variables. Now, I'm not going to go too into depth why we know this is possible. You just kind of have to take it on my word that this is possible. But we can essentially come to the conclusion that we can take the wave equation and we can separate it, uh, or we can decompose it into the product of two equations. So first, we get little psi x and 5t. So the wave equation is going to be equal to the product of these two using the separation of variables technique. So this side is the time independent side. As you can tell, it only depends on x. And this is the position independent side because it only depends on t. So recall this is just the general form of the Schrodinger equation, um, completely laid out, not simplified or anything. And from here, what we want to do is we want to plug in the product for the big psi. So we're going to substitute it in, and this is what we get, which is obviously a mess. Now, the first thing you should notice is with the partial derivatives, we can take out the 5t's, we can take out the 5t here because it's a partial derivative of x, so it doesn't even depend on 5t. So we can take that out. And over here, because this is a partial derivative with respect to t, we can take out the psi of x. So then we're able to get this equation with these taken out. And notice we can even eliminate the fact that it's a partial derivative because this equation only depends on x and this equation only depends on t. So next, this is the key part. This is the separation of variables technique. So what we want to do is we want to take each variable and get them all to one side. So how we're going to do this is we're going to divide this side. So pretty much you want to divide both sides by psi of x and both sides by 5t. And what this will do is this will take out the phi here, take out the phi here, and put a phi here. 5t here, right? And if we divide both sides by psi of x, this will take out the psi here, take out the psi here, and this whole quantity will be divided by psi of x. So this is what I mean by that. As you can see, there's no more t's on this side, no more 5t's on this side, and there's no more psi of x's on this side. So we've separated them. Now, this is the next crucial part. Because both sides depend on different variables, they must be constant. So we can choose like some arbitrary constant or arbitrary name for this constant g. But because both sides depend on separate variables and they're equal, they both must equal some constant g. You might have to kind of think over that a little because it might not be super straightforward, but if you just think it over a little, it'll make a lot of sense. So we're going to just focus on time now. So we're going to take this part on the right here, and we're just going to focus on this part right here. So breaking it out, first thing we want to do is get this psi of t in the numerator. We want to get it out of the denominator here. And we'll also take the I h bar with it. So first thing we do is divide both sides by I h bar. I did a little thing right here where if you have I in the denominator, you can put it in the numerator and take a negative one out front. And that's just a property of the imaginary number I. And then we can multiply through by 5t to get this. Now, using differential equations, you should recognize, if you're familiar with differential equations, you should recognize this. If not, this isn't like completely necessary. That if you take the derivative of some number and you get you get itself back out with maybe some constants in the front. What that means is that the function right here is e to the power of something. So 5t equals e to the power of I gt h bar. Now, the last thing is that g equals the energy of the particle. So this I won't go into depth with because this is kind of just a very topical overview of this, but this is the final equation. Now, what's super important to note about this equation is that we did not make any assumptions at all about the conditions of the particle in the wave and what it had to interact with. So this time solution has to apply to every equation because we made absolutely no assumptions. We made no assumptions and we still got this. So whenever we break the equation down to this, we always know phi of t is equal to this. Now, psi of x is going to depend, usually it's going to depend a lot on the potential equation, but we always know that phi of t will be this equation. And as long as we can get the energy somehow, we will be able to use that equation, which is extremely powerful if you think about it, or extremely useful, that we don't actually need to know anything about the equation or the conditions to be able to get the phi of t. And that's pretty much the gist of the time-independent Schrodinger equation. Thank you for watching, and I hope that was helpful.